Hello again, this is the last of our practice problems with the Hardy-Weinberg principle, and we're ending off with beans. They say a farmer planted a bunch of beans, and when the seeds sprouted, a few were albino, most were green. And they tell us the albino is a recessive trait in case we were uncertain about that. So big G shall represent the green allele, and little g shall represent the recessive albino allele. And here's the Hardy-Weinberg formula written out. You're probably pretty familiar with it by now. P squared will be the double dominant beans, PQ will be the heterozygous beans, and Q squared will be the homozygous recessive beans. Now, a new thing here, they do not give us the percentages like they've been doing. We get to work those out ourselves. They say there were 192 albino beans and 2,880 green beans, which makes a total of 17, carry a 1, 0, 3,072 beans grand total. So that means the greens represented 2,880 out of 3,072, which, if you divide it out, goes out to 0.9375. 9375 is the frequency of the dominant. That's the one that isn't terribly useful to us because it's made up of both of these groups and we don't know how it breaks down between these two groups. So always nice, better to know than not know, but we're not going to be making a lot of use of that number. The good number is that there were 192 albino beans. And we like that because an albino has a definite genotype. It has to be little g, little g. That's the only way a recessive trait gets to show. And if you divide that out, you get 0.0625. That's the frequency of the recessive genotype down here. And now that we have it, we can start doing our usual number crunch. So this part here, this was a little bit of a waste of time because really it was the Q squared that we needed. This is the calculation that you would have to do to get going. 192 seedlings out of a grand total, when you add these up, of 3,072 beans. So, given that, here comes the routine math. Q squared is 0.0625. If we square root both sides of this, it'll unsquare the Q and give us, I think that square root's just 0.25. Yep. Q is 0.25. P and Q have to add up to 1, so P would be 1 minus 0.25, which is 0.75. You can add those together if you like and confirm that they do indeed add up to 1. And now that we have that, what do they actually want? Find the homozygous frequency for the production of green chlorophyll. So what is the frequency of a homozygous green plant is what this is saying. This is a bit of an odd phrasing, but no big deal. Homozygous means we're talking about either green or albino, and here they say they mean the green. So the homozygous greens are P squared, which would be 0.75 squared, which is going to be just over 50%. What is that? 0.5625. So you could round that to 0.56, or you could say 56.25%. I'm not sure which of these they meant to round to 2 decimal places, but if you got these numbers, then you're okay. The rounding is not the crucial part here. How many plants, rounded to the nearest whole plant, would the homozygous condition represent in the study? I take it they still mean homozygous green because there's 2 different homozygous groups. There's homozygous green and homozygous albino. If we're finding these, I'll calculate this 2 different ways. We've got the proportion we need here, that there's 0.5625 of all the seeds were homozygous green. So forgive me while I blow this up. One way to calculate it would be to say that there were 3,072 plants and 0.5625 of them were green. 3,072 times 0.5625. This is the good thing about decimal percentages decimal frequencies is that they're very easy to use. You just do the whole number times this frequency and it tells you the number of members of that subgroup. In this case, 1,728 green plants. The other way you could set it up, if you like cross-multiplying, and I do, is you could take this percentage, 56.25% means 56.25 out of every 100 plants are green. And then the question is, how many plants out of our total of 3,072 are green? Okay. So the bottom numbers both represent the whole group, and the top numbers represent the fraction of the group that has the trait we're talking about, in this case green. If you do that, you'll go 56.25 times 3,072 divided by 100, and if all goes well, that should also give you 1,728 green plants. So if they meant the green plants, then this is the answer. Now, if by this they meant the homozygous albino plants, then that's already been given to us. They told us there were 192, so that's another reason why I am pretty sure they wanted us talking about the greens.